So, what you saw there in the intro was called Helmholtz resonance. When air is blown over at the top of the flask, this turbulent air moves the entire air column inside the flask. The top, where the neck is representative of a mass, and the bottom of the flask is like a spring. When this spring mass system reaches its natural frequency, you can hear the resonance sound. This equation tells us how the note or frequency is dependent on the geometry, such as a larger cavity volume lowers the pitch, or a wider neck raises the pitch. For the rest of the video, however, we'll be focusing on a more specific case, a closed-end uniform tube with a standing wave resonance. This simpler formula shows how frequency relates to the length of the tube and also how many modes of standing waves is inside the tube. N equals 1 is the fundamental frequency, and any n integer beyond that are just harmonics. Here's a visual of the standing wave. Observe the area in which the gas expands and contracts, creating zones of low and high pressure that the gas parcel oscillates between. Remember this behavior for the gas as we continue to explore thermoacoustics dynamics. Generating sound from resonance inside of a tube isn't limited to just blowing over the top of it. It can also be done by adding heat into a specific spot and taking heat away at another. This is how we can generate resonance by using thermal energy. Here we see that the thermal gradient is the key to thermoacoustics. Heat in is coming from the fire approximately 1/3 of the way up the tube, and the wet paper towel is to cool the expanding gas from where it's heated, rejecting it to the environment. Now we can instead induce the air oscillation with a diaphragm, and it will create the same oscillation of high and low pressure. I am showing a very simplified one-node animation here. Alone, it does nothing. The oscillating gas will just reach equilibrium back and forth like this. So we insert what is called a stack. The stack is an array of fins spaced out so that there's air pressure that can move in between them easily, but the stack is made of a non-conducting material so that there's the temperature on both sides that can be different without it conducting within itself. So the way the stack enables a temperature gradient, as we've seen before, is as follows. From ambient, the pressure rises at the top and the gas heats up. The stack steals some of that energy and raises its temperature before the gas decompresses back down through the stack. Then, after the pressure decreases, the temperature goes down below ambient and the cooler air cools the bottom of the stack. This use of the stack and sound to compress and expand the working fluid is the unique proposition for thermoacoustic refrigerators. Now, how do we use this for refrigeration or cooling in practical engineering applications? Heat exchangers can be attached to each end of the stack on the cold and hot end. The hot end is rejecting the heat to the environment, while the cold side is attached to whatever you need to cool, like a sensitive sensor in space. And that's it. Thermoacoustic refrigeration is amazing. The unique part of not having a moving part in any of the heat transfer regions makes it ideal for dangerous to maintain situations or remote locations where that's not possible. It makes maintenance and repairs unnecessary. This makes it perfect for applications like satellites, and specifically the James Webb Telescope used this technology to cool its camera, specifically called a pulse tube cooler. So, I hope you learned something new about thermal acoustics today. With that, I hope you have a great summer, and bye-bye.